My talk will probably be a little more technical than the previous talks. Asking a professor, even a retired professor, to speak for only 10 minutes is an interesting experiment. Let's see how that goes. Starting point is, I think we're all aware of the amazing strides that were made in NLP in the last 2 years. If you look, and this is taken from, by the way, something called the AI Index, which something out of Stanford, which we run, that tracks progress in AI. And whereas the vision community saw their ImageNet moment, as we call it, where suddenly computers caught up with human-level performance, with a 2-year lag that happened in natural language, in particular in connection with SQuAD, the Stanford question answering data set. SQuAD 1.0 was quote-unquote solved away in 2018. Then they said, oh, that's too easy, let's make it harder. Created SQuAD 2.0. Within 6 months, that was solved away. There's lots and lots of good stuff happening, very important. My colleague and friend Dan Jarafsky said there's no turning back from the neural era and all the good that it brings, but all is not good. I'm going to speak mostly about the problem, but I want to emphasize how much progress was made. Having said that, even when SQuAD 1.0 came out, my colleague Percy Liang and his student saw problems with it. The way the challenge set works, you give a paragraph such as this one and a question such as the one at the end, and you need to just point where in the text lies the answer. And what they found that with a tiny bit of distraction, the answers get totally wrong and the F-scores drop from what then was an impressive 75%. By now it's like basically 90% or 95%, whatever, dropped by more than half, or even more if you had ungrammatical sentences. So that was a first warning sign that maybe something, there's a little, I don't want to say sleight of hand, but something we need to pay attention to here. What then happened, and is still happening, is a process by which more and more data sets come up. Each data set is motivated by saying, oh, that data set, people overfitted to it and cheated, so here's a new data set that kind of called their bluff and invites the community to solve this data set. Maybe the most prevalent one today is something called GLUE. GLUE 2.0 is called Super GLUE. It's a collection of 8 or so different data sets, including word in context, which I'll just, as an example, speak about in a moment, and the Winograd schema, and many others. Allen Institute put out several, for example, ProPara, kind of understanding scientific processes when describing text. And so, for example, word in context, these are pairs of sentences. They have a word in common, like bed in the first pair. And the seemingly innocuous test is just tell me, is this the same or different sense of the word bed? The bed where I sleep, or the river bed, for example. Don't tell me what it means to be the same, just tell me that it's the same or not. What's happened with these 3 and many other data sets is that initially the old algorithm did not do well, significantly less well than humans. And then within nanoseconds, or at least months, they did well, better, or almost as well as humans. And one's reaction might be, well, that's great, we're in good shape. Every time there's a problem, we solve it. But we solved that new problem that showed up. And when you look deeper, you ask yourself, did I really solve the initial problem? The people in the community are well aware of it. Here's an example of work by Tal Linzen from Johns Hopkins and his students. And they have a very nice title, Right for the Wrong Reasons. What they did was they hypothesized that the systems that work for shallow syntactic lexical reasons that exploit the patterns in the data, but don't really understand what's going on, and therefore don't transfer when you go to other domains or try to apply more broadly. Specifically, they hypothesize that there are 3 heuristics that the system latch onto. For example, lexical overlap. This is, the task here is textual entailment. Does this text entail this other text? And for example, they said one heuristic that the system exploit is that the premise that the where's my mouse? Do I have a mouse? Oh, there we go. I hope I don't need it again. Oh, what do you want me to just use this instead? Okay. So for example, if the hypothesis consists of words that appear in the premise, then the system tends to predict that, in fact, entailment follows. And so they had 3 such heuristics, and then they did something very clever. They created a data set in all of which one or more of the heuristics hold, but in half of them, the entailment, in fact, is the case, and in half of them not. And they showed that when entailment is the case, almost without fail, the systems, all the leading systems, predict entailment. And when the entailment does not hold, still all the systems still predict entailment, which validates the hypothesis that in fact something much more shallow is happening. And the conclusion of this, we should take even the successes with a grain of salt and understand there's a lot of overfitting going on here. So when you zoom out and you say, what do AI systems understand today? It's not something that your 5-year-old understands. If you go to your kid and he tells you, Danny hit me at school, so I hit him back, but the teacher only saw me hitting him, and so she punished me, it's not fair. It's something every 5-year-old understand, and there's no machine that can come even close. So why and what to do about it? Some people say, just stay cool. All you need is more data and more statistics. Before we poo-poo this away, we should acknowledge that we're all surprised by how much you can do with neural nets and a lot of data. And, who knows how many TPUs. So it's not something to sneeze at, but some people believe that these approaches will hit a glass ceiling. And here's some evidence for it. This is something that our CTO gave me. If you look at BERT, this is BERT large, not the biggest, but a pretty big BERT already, and ask him, so BERT is a masking task. For example, you say, I ate a something, and you mask the word chicken. What will it predict? Lots of reasonable stuff, like sandwiches and burgers and steaks, but also I'll eat a plate, I'll eat a fork, I'll eat a spoon, I'll eat a quarter, I'll eat a brick. While these are smaller probabilities, when you sum them up, even these here are more than 10% of the probability, and lots of other food stuff that you can eat doesn't appear here. Another example, maybe even more telling, is I flew to New York and you mask too. What will BERT predict? Almost half the math, more than half the math goes on New, because in the corpus, it sees New York very often. So obviously, BERT and its derivatives or cousins do a lot of good stuff, but they also clearly are doing a lot of shallow statistics and questions what to do about it. One approach is to say that semantics matters, and semantics won't just arise ex machina, and let's put it into the systems. So here's an example of something we did, and we released it last August. If BERT doesn't understand, it can predict words but doesn't understand their senses, and it was already mentioned, I think, the talk before last, is that language is very ambiguous, and particular words have multiple senses. A few words have like one sense, but some of them have 20. Let's retrain BERT. It's pre-training stage. train it to predict not only the word, but also its sense. What does that mean? So it's a long discussion, but if you know WordNet, we appeal to WordNet, look at the super senses, and use that as for supervision. Long story short, system works. How does it work? How do we know it works? Because, for example, you go to the same word in context data set, and again, not that we're a big believer in data sets, but if you go to that, just this joint BERT became the leader, at the head of the leaderboard of that challenge set. That's an example of very limited form lexical semantics and how this can help if you, in a clever way, put it into the system and merge it with neural nets. And so that's a question I think all of you need to ask yourselves. You know, which camp are you in? Are you in the just, you know, more camp? Or also more and different camp? Just more muscle, or also, you know, more semantics? At I-21 Labs, we're clearly on the semantic side, and this is kind of the picture that drives us. If you look back to the 80s, by the way, if you go to the same AI index, you'll see hundreds of charts and stuff, and you'll see kind of these charts that go like this. So back in the 80s, conferences were, you know, sold out like they are today, but the whole discussion was around knowledge representation, symbolic systems, and so on. Today, it's the mirror image. There's no semantics, but it's all about statistics, a lot of compute. And we believe that the third phase of AI is marrying the two. We're trying to make a contribution in that direction. Thank you very much.